Thank you, Lilith, for the introduction. Okay, so thank you for the invitation and the introduction. I will take the opportunity to present you some preparation work we did for EuroHPC for the peer review process. And I would like to start with the peer review principles, and then I will address the main access modes, extreme scale, regular access, and development and benchmark access, and will conclude with some implementation scenarios, which will come quite soon. So it's we are getting there. So actually, these peer review principles were developed since a long time. I will not go into the detail. I want just to draw your attention to the complicated process. And over the year, Praise really worked a lot in improving the peer review process and constantly improved. And for instance, some details of the review process takes much more time and effort than you might think. For instance, managing the interest. So this has something to do with the conflict of interest. So we are asking the applicants to indicate, for instance, possible reviewers for the application, as well as reviewers they do not want to look at their application. And we find that a lot of proposed reviewers actually from the applicants have at the end a conflict of interest, so that they cannot be used for reviewing the proposal. So let's start with the access mode. So extreme scale, which will be comparable with the present tier 0 Praise calls, will start basically next year. We have the regular access with less resources compared to the extreme scale, but with a faster review process, which will start actually the call should open still this month. And already in place, we have a benchmark and the development access, which are comparable to the present Praise preparatory access calls. So let's go back to the extreme scale, though this is for huge demanding projects with 2 cutoffs per year, with the award for 1 year with a possible extension, and who can apply. So EuroHPC joint undertaking defined this eligibility criteria in the access policy as researchers from academia, research institutes, public authorities, and industry established or located in the member state or in a country associated to Horizon 2020 are eligible to apply. So this is the eligibility criteria, and this will be also checked. Then here you see a diagram of the review process for the extreme scale. So there will be, of course, an admin check at the beginning, and then each proposal, 2 rapporteurs will be assigned to 1 proposal, a lead rapporteur and a second rapporteur, which will propose then the scientific reviewers. And based on these scientific reviewers, they will produce then individual reports and a consolidated report. And before this scientific review, there will be, of course, also a technical assessment by the hosting entity in order to check if this project is feasible at all. So once the reviews are received from the selected external reviewers, which are also checked part of conflict of interest, the rapporteur assess the different reviews and propose also a grading. Then in the allocation resource committee, there a final ranking of all the proposals is made or is proposed, which is then confirmed in the resource allocation panel, which proposes a list with a ranked proposal and dedicated link to the different systems available for approval of the EuroHPC governing board. So this peer review is based on the ERC process. Though the admin check is important because there are some criteria which has to be respected. So the application must be complete. The right template has to be used. The requested information need to be there. For instance, very important are the scaling curves in order to demonstrate that the code which is proposed in the project can run efficiently and effectively on the requested system. So the technical assessment actually check this if the requirements are available at the target system, and in case of doubts also the applicants can be contacted by the technical experts in order to clarify some questions. Okay, then the scientific assessment, it will be based on the scientific merit, soundness of the numerical methods, appropriateness of project timeline and resources, and feasibility of the research plan. And project from industry and public sector will be assessed based on relevant appropriate criteria. How this will be done, I will this is not yet discussed for the extreme scale process, but for the regular access it is, and I will come back to this in a minute. So I mentioned already that there will be two rapporteurs dealing with one proposal and collecting the reviews. In the extreme scale scientific track, the scientific excellence is a single decisive criteria, and different criteria may apply for industrial and public sector applications. And then the proposal are ranked according to the grade of the rapporteurs, and then in the access resource committee there are compared all together. This is the process of the access resource committee. So the lead rapporteur actually presents a proposal objectives, the strengths and weakness, and report the grade. The technical member then discusses the feasibility of the project, and if needed, the second rapporteur makes additional remarks, and then all members discuss the proposals and ask questions, and then the lead rapporteur proposes a grade, and in case of agreement, it becomes the tentative score of the proposal. In case of disagreement, there is a vote, but this happens very not very often. It's the exception. Then proposal needs to be rediscussed when similarities are found with other proposals, and the grade might be revised. Also, in case of ties, if at the end proposal reach at the very same grade, though there is again a discussion in order to rank also these proposals. And though the proposal for a decision is then made in the resource allocation panel. This is chaired by the EuroHPC executive director, and the panel decides, of course, on the recommendation of the ARC and constraints also on EuroHPC resources and administrative constraints and agreements with EuroHPC joint undertaking. And then the EuroHPC governing board should be able to confirm the final allocation. So now in the last weeks, we worked very intense on the new access mode, regular access, which should open still this month. So this is also a continuously open call with 3 cutoffs. It targets large but less resources compared to the extreme scale. And the maximum allocation will be aligned with the minimum allocation of the extreme scale access. The award will be for 1 year with the possibility for an extension for another year. The eligibility criteria are the same for the extreme scale. The important point is that a faster review process is foreseen, and Lilith actually knows very well how this is done because she led the working group elaborating on this. So the process is shown in this diagram, and I put here also how it would look like in the tool. You have the different steps of the application, from the application, the technical assessment, the scientific evaluation, the response to reviews, and response to allocation. And also here I put here, you can also opt for public services and opt for industry. What consequence this will have, I will explain in a minute. So the call will open and will continuously open with cutoffs. There will be also an administrative check, which will look for the completeness of the proposal and so on. And then the technical review will be done by the hosting sites. And then the proposals are classified to different panels, domain panels, and the domain panel chair then selects 2 panel members who will do actually the scientific review. And this is why we hope that, or why the project will be faster, because there is no need for an extensive and long search for possible reviewers. So the reviewers should be ready already and accepted that they will do reviews for the dedicated call. So they will do the scientific reviews, and there will be also, this is called rapporteur and lead rapporteur in this case for the equivalent to the reviews. And the lead rapporteur will then produce there will be a domain panel session, which classification of the received and ranking of the received proposal, and the lead rapporteur will write such a consolidated report, review report. The applicant will have then, after this review is done, the right of reply. He can reply to the technical review and the scientific review. And then there will be the so-called super panel, where all the panel members will meet and rank their proposals. And this will then lead to a ranked list, which will be approved by the EuroHPC Joint Undertaking Governing Board. And then the project, or the applicants, will be informed, and the project can start. So I told already a lot for what is written here, so I will skip this in order to save time. And I want to say a word to the award criteria and scores. So this follows very much the EC review you might know from if you prepared a proposal for a call, the Horizon 2020 framework, for instance. So there are 3 criteria: the excellence, innovation and impact, and quality and efficiency of the implementation. And these 3 criteria will be evaluated. And for the scientific track, excellence will be the most important part. For industry or public services, it will be innovation and impact. If you select if you not select the industry or a public service track, actually it's not up to you. I think it depends from where you come. If you come from a public service, you can activate the public service tick box, and then you end up in the public service track, where you have 5% of the resources reserved for this specific purpose. If you if you come from industry, or the PI is from industry, you can go there and you have 10% track reserved for industry. The 85% are distributed for this scientific track. So, and depending on the track you selected, these criteria have different weights. So, as I said, for scientific, it's excellence, and for industry and public services, innovation and impact. The scoring principles are also quite similar to the scores used in the Horizon 2020 framework program. So it goes from 0 to 5, from fail to excellent. You need to reach a threshold for each criteria at least 3, and the overall minimum threshold is 10. So this is the way how the evaluation will be done. So now let me add also the benchmark and development access. So these are already running calls, also continuously open with a monthly cutoff, depending on which track you choose. Benchmark, you have 2 or 3 months allocation, development up to 12 months. And there's a short administrative check, a technical review, and then a decision on the award of the project. So there is no scientific review on this. It's just a technical feasibility. And that's it. So this call, as I said, open continuously, already open. And after each cutoff date, EuroHPC Joint Undertaking receives a ranked list of the application to be considered for allocation. Good. The access of the new EuroHPC systems depends, of course, very much on the systems getting in user operation. I think it's also important to mention that installation, operation, and user operation are still different, and the time might be also different for this. But though the call for benchmark and development access are published and you can apply already, and very soon, so opens in September. So the exact date need to be confirmed for the regular access. The call-in should close end of October. Oh, there's June still, though it's October 21. This is then also sync with the praise tier 0 call. And then next year we expect to have the new EuroHPC extreme scale call opens March and closes also April 22, of course. And this will be then also sync with the praise tier 0 call. So that's all from my side. I thank you, and I'm ready also then to answer the questions later.
Thank you very much, Florian. The next speaker is Pekka Mannen, Director LUMI, and he will present LUMI for us. So Pekka, the floor is yours.
Okay, so good morning also on my behalf, and delighted that there are so much interested people again on the roadshow. So for those who have seen this previous roadshows, I only have some minor updates. So it's basically the same content with some updates on the schedule. But for those who haven't seen the previous roadshows, we're going to go through discuss the LUMI architecture and what kind of what do we have to offer for you as for your research, and then as a second part on how to prepare for LUMI. And like I said, so feel free to type lots of questions for me in the Google Doc. And without further ado, so LUMI is, like I said, one of those upcoming three EuroHPC flagship supercomputers, pre-exa-scale supercomputers, and unlike the two others, LUMI is a joint effort of 10 countries with strong investments and strong contributions to the outcome. And the countries are seen here, so each of them are investing a substantial amount of money and work for the outcome of LUMI, and LUMI is jointly hosted and operated by the consortium. So it's in our data center, but the user support, the governance, and many things related to it are a joint effort within this consortium. And as the similar to the other ones, so the 50% of the total cost of ownership is covered by the EuroHPC JU, and for this they will grant also the 50% of the resources via the extreme scale access now at least for now operated by Braze and available for all European researchers. And the second half is by the investments and distributed or allocated by more like local considerations up to the countries. I will get back to those in a minute, but in a way they have quite a lot of flexibility on how they want to give out the resources. But the LUMI itself, so it's going to be the fastest of the first generation of the EuroHPC systems, and like Vangelis already said, so it's going to reach the 550 petaflops plus for the GPU partition and some more from the CPUs. And perhaps like well, if you want to just compare the peak performance, it's on the clearly on the level of the fastest computers today. And we still have some hopes that it would make it to the November top 500 list, but let's see if that's really the case. But more importantly, it's going to be a very modern vanguard installation, landmark installation for supporting the convergence of traditional simulation, HPC, AI, and massive data analytics. And this is reached via the convergence of cloud computing and high performance of traditional high performance computing and a convergence of GPU and CPU technologies. So at the moment, LUMI looks like this. So we have installed the CPU partition. So it's going to be followed by a couple of more rows for the GPU partition. So they are still in the factory, but the CPU partition is there. We have started to the acceptance of the system with the couple of the first leanback results on a bit over 6 petaflop for the CPU partition, and the storage is there and up and running. And we hope to be able to start the pilot use in perhaps 1 month from now. And here you can see the data center. So it's this kind of a building within a building. So 2 stories building, where the first floor is for the kind of like a raised floor, just 3 meters high raised floor, but it's still a raised floor. And then on the second level here, you can see the white spaces here. So this space is on the second floor of this building. And underneath this one, there's all the MET is being put on like a real floor of this big hall. But to the technical details, so like I said, at the moment we have the CPU partition and the storage and the data analytics partition there in place, and hoping to get customers on soonish. Also the container partition there, and the kind of a main number crunching machine, the GPU partition, coming up towards the end of this year. Some technical details. So the storage is going to be on 3 layers. So flash, very fast flash-based access for extreme I/O needs, more traditional spinning disk raster file system, and then like a object storage service that we start from 30 petabytes and prepare to increment it whenever there's like a customer need for a larger object storage service. But it's just like a start from a, like a say let's say this kind of like a limited number of object storage capacity, and everything sits nicely in the same interconnect, same computing environment, enabling kind of like a very flexible combination of different resources for the same workflow. And some words on the node architecture. So the GPU node will contain 4 of the next gen AMD GPUs. So the MI100 is has been released, and the LUMI's GPU is the next gen version of that technology. Highly likely to be announced in this next supercomputing. So I can then I can tell you the kind of in November I can tell you also the flops and so on per node, and with one single CPU meant for really this purpose. So it sits on this Infinity Fabric mesh, and each of these GPUs will have an exclusive access to the interconnect, so they own NICs. And for the CPU side, so LUMI C, we are running the AMD Milan processors, the top SKU Milan processors, each of them having 64 cores, and we have like a various different memory configurations for the LUMI C part. So starting from the 256 gigabytes and reaching the 1 terabyte nodes. Timeline. So this is a little bit of unfortunately pushed to the right. So like I said, we are accepting at the moment the first part that contains everything besides the LUMI G, and in addition, it has something called Early Access Platform, which is like a small GPU platform for doing code coding and application enabling for the LUMI G. And then towards the end of the year, we will start installation of the second phase, and I would assume that being available for users in the first quarter next year. And it's going to install the LUMI G and upgrade the network of the LUMI C partition. And we are still pondering whether we want to do some kind of a phase 1.5 in between, but you will be updated via the national competence centers on how we're doing. But this is the current thinking at the moment. Unfortunately, we are really hitting on the global shortage of semiconductors, and then that's why the second phase has been pushed from the little bit further that I last time speaking I was saying. LUMI hardware side, so we also, well, we won't make it to the #1 in the top 500, but where we want to be the #1 is the user experience. So we are at the moment pretty far away on the kind of different swimming lanes on what we want to add to the stuff that we buy from the SPE. So we want to support pretty seamless higher this kind of like a GUI style interfaces, like Jupyter notebooks, RStudios, and so on, to sit on top of the computing resources. We are planning the ISV software budget at the moment, or the software stack or this portfolio at the moment. We are looking at the concept called datasets as a service, where we have, in addition to software, we would have like a large datasets readily created on the system. And also we are working on how do we could avail or be enable using GDPR subject with like a sensitive data or say IP critical data on the system. LUMI user support, this is a kind of a novel concept that we are very proud of, is that we didn't like put the support team only to CSC, but we wanted to do as a joint effort. So what we're doing is basically have one expert in each of the LUMI countries, and that works as a coherent team. And then they have kind of like access to their local resources, and they can collaborate with your HPC competence centers and so on. And we have managed to gather a really skilled and seasoned group of experts. And in fact, LUMI user support team is already providing user support, so you can contact them already what comes to the application preparing and things like this for LUMI. So if you go to LUMI website, you can just like file in support requests already now if you want to get some assistance for preparing applications or benchmarking it or something like this. So other than besides that, just like I say, a few words on I think I have a few minutes time, so few words on how to prepare for LUMI. So let me just like start from recapping the capacity. So of course it's starts from the extreme computing capacity. So we hope to be a platform for solving computational problems that are just intractable at the moment with these resources from consisting of GPU and CPU resources, and have this kind of spice or added value from the large inductive usage partition for very intricate visualizations and data analytics and so on. It has a very large stack of visualization GPUs and a humongous shared memory on the machine. So we do hope that nobody has a data bigger than those capabilities. The scientific software itself stack can be an asset for many research cases. Also the data management via the object storage service and the cloud partition. And gray here, of course, we want to, LUMI is not complete yet, so we want to add capabilities, especially related to the quantum computing on LUMI later on. Not part of the deal, but with some other resources. And then we also have aspirations of providing some like a emerging technology testbeds also on the LUMI environment. So how do you get access? If you're based in Sweden, you are in a good hands. So Sweden is part of the consortium, and therefore Sweden has more or less free hands on allocating these GPU, CPU storage resource pools. So the resources or the accesses are applied as a combination of the three pools. This will apply also to the Brace projects. And basically with this, everybody are on the same equal footing on the system. So all users who have a project can apply the system within the limits of the patch-up policies. And we have decided to use the same taxonomy also for the national allocations as EuroHPC JU is doing so, but with so that also regular access projects can be granted. So smaller scale projects can be granted to the system. And reminding that people in the Swedish institute, so you can apply either from the national quota that Sweden has or from the EuroHPC quota, or why not both? So just reminding that even countries part of the LUMI consortium are eligible of applying from the JU side. And also in addition to the user, this kind of like a project-based access, we have this kind of a fast track director share for something very mission critical, where we just can we have some resources set aside for this kind of a director's discretion style accesses. Few words on the programming environment side. So LUMI, like I said, is heavily relying on the AMD technology. So the stack is a combination of the AMD's Open Compute stack and the Cray programming environment. And if you have used the Cray systems of the XC line, you kind of know what to expect. So there will be the familiar Cray compilers, libraries, tools, performance analysis tools, and the debuggers and so on. And if you want to read more, just visit the website, and there's a blog, 2 blog posts introducing the topic. So quick thoughts on how to prepare the upcoming applications is that, well, it's a GPU-based system, of course, so you need to have some tactic for GPU accelerating it, but also reminding that it's very flexible in terms of combining CPU and GPU nodes to the same workflow. So perhaps only the most computationally intensive parts of the applications need to really GPU enabled. Also, one of my, perhaps I may have a bit biased here, but it's just my opinion, but I would still like a way for this performance portability. So high-level libraries, domain-specific languages, and so on, something worth looking at if you are facing a kind of lots of conversion work or accelerating works. And if you're in a situation that you already have a GPU code, so written with CUDA or OpenACC, I would recommend of transferring. CUDA code need to be transferred to HIP. OpenACC is in principle supported, but I think the performance will be, at least in the beginning, better with OpenMP5 offloads. But especially for this conversion, there are pretty nice automatized tools on the system for doing this conversion, as HIP is basically a re-implementation of CUDA by AMD. And like I said, so we will offer this kind of like a early access platform for that has the current gen GPUs for doing this work. And if you don't, before that, while waiting for the access, you can do the HIP porting already on it's an basically hardware agnostic, so it can be done on other platforms too. So basically, this was what I had in mind. So welcome to the EuroHPC era. So basically, we are having a golden age of scientific computing starting in Europe. So there's an unprecedented amount of computational resources and capabilities in Europe now. So not only very interesting and ambitious computer installations, but also lots of resources for competence building and user support and this kind of a community engagement. And I was proud and happy to present LUMI, the Queen of the North, which is designed for this kind of like a broad user base and for enhanced user experience. And as a take-home message, that is, it will be based on AMD GPUs, and which needs some preparatory work, but I'm sure it will pay off. And it's not an experimental or esoteric system in any manner, but it's a robust production system that strives for high SLAs. So it's time to get ready. We are soon online, and thank you for your attention, and remember to follow our journey on the social media or via our website. Thank you.
Thank you very much, Pekka, for this presentation and for the update. I would like to use this 5 or 4 minutes to give the floor to one of my colleagues, Roberto De Remigio, as he has a little bit of an information for Swedish users of LUMI. So we will just do a little step out of the program for 2-3 minutes. So Roberto.
Yeah, thanks, Heli. So we have prepared this little website together with colleagues at CSC that should help you understand the different ways you can port existing codes to LUMI. So this is a little interactive thing. So if you click around, you kind of will see useful information about LUMI, or links to useful information about LUMI, and also about paths to port your code to these large machines that are being made available through the EuroHPC joint undertaking. So for example, you see here, you can choose whether your code already runs on GPUs or whether it does not, which language your code is written into, for example, C++. And then, as Pekka was pointing out before, in C++, you have different high-level parallel programming libraries that you might want to use to port your code. And these libraries or frameworks, it's more correct to say, for example, Sico, Cocos, or Alpaca. And if you go to the last page, you will see a list of links to materials that you can use to learn more about these frameworks and how they can help you port your code to LUMI. And of course, there's info on how to get in touch with us at the ENCCS if you would like help with porting your code, or if you're curious about any of our training events, for example, on SQL or HIP, OpenSCC, OpenMP for GPUs, and so on. So this is all I wanted to say. I will put the link to this website in the chat so that you can explore on your own. And yeah, I hope this is useful.
Thank you very much, Roberto. The link is in the chat, and also this tool is on our webpage, on the homepage, so anyone can just go in and access and try. And with that, I would like to continue our journey through the EuroHPC systems. So the next speaker now is Fabio Pitari, from HPC specialist from Cineca, and he will introduce Leonardo. So Fabio, the floor is yours.
So, welcome everybody. I'm Fabio Pitari from Cineca. I wanted to give you a quick overview about Leonardo, which will be our next EuroHPC system, supercomputer. And in order to do this, I want to give a brief introduction of how we organize usually our clusters inside our data center. So, usually we have two different classes of cluster, at least two clusters in our data center in Casalecchio. The first one is the one which we call Tier 0, which is our flagship system. So basically it's the one that gives us the biggest computational capacity. And currently our Tier 0 is Marconi 100, which was ranked at its best at 9th position on the top 500. And then we have also another Tier 1 cluster, so something that we use for small project or for essential services for public institutions like weather forecasting or pipelines for scientific centers. And together with this, we have a cloud infrastructure in order to manage data repositories and big data analysis and something like this. So this has been always our organization, more or less. And in particular for Tier 0, if you look at the energy consumptions of our last two Tier 0 cluster, you can see that, for instance, the current one, Marconi, has power consumption of 4 megawatts, whereas the previous one, Marconi, has something like 3.5. So something very close one to each other. But we somehow reached the threshold of our data center. So for the next pre-exa-scale system, Leonardo, we will need to move away from our structure. So I will show you a little bit about what of the building that we are going to use in here in Bologna. And because Leonardo will need something around 10 megawatts. And so about the procurement, Leonardo was supported by the Leonardo Consortium, which was formed by several different institutions. First of all, it is confounded by EuroHPC and the Italian Ministry of University and Research. And the hosting site were Cineca together with the ENFN in the new Technopole that I will show you in a while. And CISA was the last Italian partner, but there were many other partners. In particular, there is the Greek Ministry of Digital Governance, the Slovenian Ministry of Education and Science, and the Hungarian Ministry of Innovation and Technology, the Austrian Ministry of Education and Science, and the Slovak Ministry of Research and Science. So this was the consortium that supported the application for Leonardo, and the procurement started in the beginning of 2019, and in the end, the winner was Atos. So everything will be based on the Butsequana racks of Atos, so the XH2000. So, and every rack will be cooled by direct living cooling. So actually not every rack, but 95%. So we will keep out the input-output racks. Beside them, everything will have possibility to be cooled by direct living with a direct liquid cooling system. The inlet temperature will be 37 degrees, and everything will be connected in a Dragonfly Plus topology. I will show you later some details. And the energy management will be optimized by some Atos tools, in particular by the pool energy optimizer and pool dynamic power optimizer. So the main idea of Leonardo was to have in something like this two big modules to divide basically the cluster in two big partitions. The first one would be the booster module, in which basically most of the computational capacity is achieved. So it's composed by 3,500 more or less nodes, in which the core of the computational capacity is given by 4 NVIDIA Ampere GPUs. And the target is to have 204 petaflops in the sustained HPL. But together with this, there is also a data-centric module which allows to reach a smaller computational capacity, so something around 8.9 petaflops actually in sustained HPL. But the computational core is 2 Sapphire Rapids CPUs, but the idea is to manage a different kind of workflows related to data. So we have a bigger amount of RAM, which is 512, and of DDR5, and an NVM unit for each node. So everything will be connected through a low latency interconnection with 200 gigabits, and also with an Ethernet connection of 100 gigabits. But everything will be connected also to the storage, and we specified that we wanted to have two kinds of storage: a fast one with a smaller capacity, 5.4 petabytes, but with a strong bandwidth, and a bigger one for storage with a bigger amount of capacity, and should be something like 106 petabytes. And the access will be given through 16 login nodes, and which are similar to the booster module, basically, and 16 Visual JSON nodes for implementations of front ends and graphical user interfaces. So I will show something about the booster module in particular. And our starting point was the current IRZO system, which is Marconi 100, in which we try to understand which are the main limitations of the current machine that we are using as IRZO. And Marconi 100 in its board has two different sockets with the Power 9 CPUs. And on each socket, it has two NVIDIA V100 GPUs. And everything is connected through NVLink. So basically, you have a fast connection between a single socket and two different GPUs. But and you can easily do GPU direct between these two GPUs, but you cannot have a GPU direct with a fast connections between two GPUs connected to a different socket, because we have a bottleneck among the sockets or among the connection between the GPUs. So basically, GPU direct, which would increase the performance a lot, it was not optimized in such kind of architecture. So our idea was to improve, to have a connection with our current architecture, but to improve this kind of system. So the blade of Leonardo, which is called Da Vinci, has been designed ad hoc from by Atos. And the idea is to overcome such limitations of Marconi 100. So we have 4 GPUs of milliampere, and all of them are connected through NVLink with an all-to-all connection. So we have 200 gigabytes of connections among all the 4 GPUs. Then they are connected to the single socket Ice Lake CPU through PCI Express with 16 connections. And in order to improve furtherly the GPU direct possibility, we have also an HDR100 adapter on each of the GPUs of the single GPU on the socket. So you can have basically a GPU direct connection also from one board to another board, which hopefully would increase a lot the possibility to increase the performance. And the latency, so the main difference with respect to Marconi 100 is that the latency among the 4 GPUs is always the same, and we have a better ratio between CPU and accelerator and a better bandwidth, because both in the case of GPU bandwidth, but also for the single NVIDIA GPU, because it has a more modern technology. So this is basically the booster partition. And as for the data-centric partition, we have a different kind of socket. We have 2 different sockets for Intel Sapphire Rapids, and a bigger amount of RAM, but in particular, we have also an NVM unit on each of the nodes for the data-centric partition. And for the storage, I will show you later that we have some further improvement for the fast storage. So the interconnection will be, as I said before, the Dragonfly Plus topology. So it's more or less 23 cells, and 19 of them will be for the booster module, and in each cell you have a FAT3 topology and level 1, 3 level 1 switches for each cell, and a level 2 switch for each of the nodes inside the single cell. So we have an all-to-all connection among the cells and FAT3 topology inside. And as for the storage, we have, as I said before, 2 different storage. The first one will be the fast tire, which is basically optimized through the DDN IME tool, which will allow us to use the NVMe to store metadata and data buffers on the fastest kind of storage, the NVM. And all the rest of the capacity of the 5.4 petabytes of fast tire will be given by SSD storage. So the idea is to reach an aggregated performance of 1.4 terabytes per second in read and write bandwidth. And everything will use the Lustre file system. We will have also a storage capacity tire, which will have a slower bandwidth because it's not based on SSD, but on normal HDD system. And so the bandwidth will be lower, will be around 740 gigabytes. But it obviously guarantees a bigger capacity for storage for the users. So the idea was basically to start from what we already achieved with Marconi 100 and to improve it, but also to expand in some different direction that we didn't explore yet in our current cluster. So First of all, we wanted something that we wanted to optimize the possibility to have GPU direct as we had in Marconi 100. In order also to improve application for artificial intelligence and engineering and many of the applications that are currently running on Seneca clusters. But what we wanted to achieve, as Vangelis said before, is also to have the possibility to explore cases of urgent computing as happened during the pandemic. So in particular, during the pandemic, we had to manage the many of simulation related to COVID research, and they were managed mainly by the Accelerator for COVID project. And this is something that was rather new with respect to what we were used to. So it's something that with such a huge machine like Leonardo, is something that we wanted to somehow improve our approach on cases like this, hopefully not for sad occasions, let's say. And something, there was something new also related to the login approach, because this is the first time that we have so many visualization nodes. So we want to have a high-level interface for the users for on our 16 visualization nodes. So it's something that we are trying to explore on our Carrier 1 cluster, Carolina 100, and we want to improve it in the case of Leonardo. And also for more incoming new technologies like quantum computing, which requires a lot of simulations on its emulator on emulators that requires a lot of computational output. So it's something that Leonardo can explore much better compared to our current clusters. So the remaining question is where and when we will put everything on. So as I said before, we need to move away from our data center. So the timeline is more or less something like this. The booster module will be the first one that will be put online. So we hope to have the installation done for January and next year. So the organization should start in the end of this year, and we would like to start the pre-production phase in the beginning of the next year. And hopefully, when we have completed the tuning and the software installation, we would like to have everything up and running before June of 2022. This for the booster module. More or less, the timeline was the same for the data-centric model, but maybe a little bit delayed with respect to the booster one. So this is our idea, but we want also to move to the new building, which is the Tecnopolo di Bologna, so Bologna Tecnopolo, which is something like this. Maybe I can show you this before. It was formerly it was a tobacco factory, basically, which was closed in the 70s, I think. And so Emilia-Romagna, the region in which Bologna is located in Italy, gave the permission to refurbish the building, but respecting some historical constraints that were related to the cultural heritage of the site. So basically, the site is like this. We have 6 buildings like this. We call them barrels, basically, botti in Italian. And in each of these 6 buildings, we are planning to put some. It is planned to have an Hpc system inside, but only 2 of them are for Seneca and ENFN for hosting our clusters. In particular, this one is the one in which Leonardo will be located. The other one, it's empty, and it will be used in the future for expanding our infrastructure and for future clusters. And the other 4 are for ACMWF, which is moving from return to the same site, so to Bologna's Technopole. So these are the main buildings in which HPC systems are located. This is the section of the building in which we will locate Leonardo. And the idea is to connect the current data center in Casalecchio with a fast connection of 200 gigabits per second to the new Technopole in Bologna, which is quite close, but not so close actually. And to have a fast connection through Geant via GAR from the Bologna's Technopole. So besides the barrels, the buildings in which we will put the HP system, there are also other buildings for people that will work on the HPC system. There's a loading bay, there's security, and so on. And there are also some other buildings for some research institutes like CNR, which will take part of the buildings. And the buildings related to Leonardo has been calculated a PUE of 1.1 for our machine. So it's been certified this kind of values, and these are more or less the power management that we are planning to have in the future. So basically, this is the current situation. So Leonardo will take more or less 10 megawatts for its IT load. And it's located in a single building of the 6 that I showed you before. So far, the cooling system with the direct liquid connection, the direct liquid capacity can cover more or less 8 megawatts of this power capacity. And the other one will be covered by air cooling connection, but with an air cooling system, traditional air cooling system. And this air cooling system will be will have a 3+1 redundancy. So it's something that we might think to expand actually. So basically, the idea in the future, the idea is to have a modular system that we can think to expand in the future, both in the direction of expanding the direct cooling system, or expanding the air cooling system. So in the future, we hope to reach the power supply of 20 megawatts, not 10. By using the other building in the same site, and we might either to improve the capacity of the direct cooling system by reaching something like 16 megawatts covered by the direct liquid cooling, and or maybe we might improve the air cooling system, maintaining the 3+1 fashion. So the air conditioning system would be maintaining that 75% of the percentage of its peak capacity. And this is what basically I said just now. So one of the strategies that we are thinking is to improve the direct liquid cooling, which means that we will maintain the 3+1 redundancy for the air cooling one. Whereas in the case in which we expand only the air cooling system, we will keep anyway the 3+1, but we'll improve the capacity of the around 12 with respect to the current 6 megawatts, which is covered so far. And I think that's it. So I would like to thank my team leader, Mirko Cestari, which basically brought all the slides by himself. And I thank you for your attention.
Thank you very much, Fabio. It was interesting.
So I'll give you words on Hpc Vega System, and with a bit of a focus what was done recently, because it was the first system to put in the production in April. So the Vega Hpc is basically roughly 1,000 node HPC with a smaller partition for GPUs. About 60 nodes are GPUs. The rest is CPU. And while the performance of both partitions in terms of petaflops is roughly the same, we also have a significant storage, let's say for a petascale site, which is 23 petabytes of raw large capacity storage, and then 1 petabyte of fast cluster storage. So the design goals were to build a general purpose HPC, which will be useful to all communities. So apart from the standard EuroHPC requirements, let's say on HPC, compute intensive, HPDA and AI workflows, we wanted as well to have extreme data processing capabilities. So with really large data workflows, even from wide area network. And of course, our plan is to go to the hyperconverged network in the near future. And we also wanted to provide a remote access for job submission and data access. So the system is a standard liquid cooled Bulsa-Quana HPC. Here are some details on the CPU nodes or GPU nodes, and when the blades are put in the rack. The cooling infrastructure is designed for high temperature inlet workflows, so it can go up to 40 degrees. And the cooling is also managed by the Boole energy optimizers that were already effective this year when it was highly hot. Then we have to reduce the processing power of the HPC, and this is now automated. The storage nodes are of 2 types. So the cluster storage are 10 boxes that provide around 400 gigabytes per second of throughput, and the large capacity drives are based on Ceph. So the network is built around two layers. One is the InfiniBand HDR100, which is used basically mostly for compute and cluster storage access, and 100 gigabit Ethernet, which is used for service partitions, Ceph storage, and for the outside access. Both networks are bridged with Mellanox skyways, so InfiniBand to Ethernet gateways, with a capacity of 3.2 terabits per second. And the current wide area network connectivity is about 200 gigabit per second to our national provider, Arnes. And it's at the moment is 100 gigabit to the outside world, so let's say to Xeon, LEC1 network or Prace network. So the performance of the CPU partition is 3.8 petaflops for computing nodes and 3.1 petaflops for GPU nodes. The Ceph is configured for the usage of CephFS, so the POSIX 5 systems, then the remote block devices, so images that are served to other services, and Rados gateway, which is being set up these days as well. And one important issue here is that the useful capacity in the mode we are using, so this is erasure coding 16+3, is roughly 84% of useful capacity versus raw capacity. The research domains that we target are several ones. So we cover here all the fields of science that are relevant for Slovenia. And apart from that, of course, all the sciences that are targeted by other EuroHPC users. So for example, we have non-equilibrium quantum statistical physics, then theoretical and experimental particle physics, machine learning as everybody else. The bioinformatics, biomolecular and material simulations are quite extensive. Fluid dynamic simulation in reactor physics are quite important because we still have a working nuclear power plant, and this HPC will be extensively used for the studies over there. Then we have quantum computational chemistry, typically used by material sciences with a framework like quantum espresso. A lot of our science is involved in astrophysics and satellite astronomic image processing, so in participating in several large international collaborations. Medical image processing, genomics, and proteomics is also quite important for us. Apart from that, we have also strong language, model analysis and text analysis, so not just spoken language, I mean, in this case. And this was also actually exploited by the Swedish Royal Library recently by the through the development access. So the current users, the users we have up to now, so just to give you some numbers for a feeling what is the usage of EuroHPCs up to this point, we have roughly 85 user accounts. Let's say 15 of those are of the administrative nature and of the high-level support team. And we also, in addition, we also have 15 remote submission accounts. So the people that use these accounts are actually not, they do not log in on the machines, but they can directly submit their jobs to a special service through their laptop or desktop or from their remote institution. We had around 30 users from the development and benchmarking EuroHPC calls, so up to now 90 applications for resources altogether. And those calls actually quite from various communities. Most of them were targeting, of course, were targeting GPUs, but many are still relying on CPUs. It actually depends very much on the application nature. And they come from physics, chemistry, material sciences, mathematics. So quite a wide area of interest, let's say, initial interest into the EuroHPC calls. So we allow for basically the same thing as Luma did. So for all job types, so from single core to the systems that through the jobs that can use most of the HPC. We have a lot of single core high memory jobs, which are typically used for when one develops the algorithms, the new algorithms for machine learning or artificial intelligence. We also participated in the folding at home for COVID-19 research with our GPUs when the system was not fully used yet. So let's say in the opportunistic mode. So and the system was quite highly ranked at the time in the first, between the first 10 contributors. We have a lot of single node jobs, and those are typically the ones that use GPUs. Many applications are still not quite tuned for parallel execution. So even 4 GPUs on one node are relatively difficult to exploit by, let's say, by many applicants. We have, of course, also several parallel jobs that can use up to 20,000 cores. I think this was roughly the order of magnitude that we achieved in the last few months. So even so, probably we'll have even larger jobs in the future. We also have extreme data processing and Monte Carlo simulation jobs that I'll explain a bit later. So the resources are not yet fully exploited by individual user applications, let's say for by the official granting of the resources. So we are in the past, or even now as well, we are trying to backfill the unused resources with the LHC data processing, analysis, and simulation. So we run production for the experiments in particle physics. So overall, the usage in the last 60 months was higher than 90%. So just to give you a hint how the Atlas, or the, let's say the particle physics, experimental particle physics is using our resources at the moment. So this is just a figure of an event of Higgs discovery or a Higgs event that Higgs boson production that was this was measured a few years ago. So in this case, we had to equip our HPC with several additional services to make it transparently being integrated into the, let's say, distributed computing environment. So we are connected with a job management infrastructure, which is, sorry, what did I do? You can still see it, right? Let me stay in this mode. Okay, sorry.
Yes.
So we have a workload management at CERN that controls the job submission and execution, and we are using the NGGF Tier 1 distributed storage. A few words on that a bit later. So we have several services that control data staging, data transfers from the outside world. We also have several HTTP proxies that serve the database access to the outside world through HTTP protocol, right? For the nodes, right at the moment, we have to use the external connectivity through NAT, but later on it will be used directly by the Skyways. So on the nodes, we have to additionally install CVMFS distributed file system, which can provide transparent software distribution, and is actually used in Slovenia for the other communities as well, so that the people do not need to install their software locally. We are exploiting, of course, local NVMEs for local scratch, and all these workflows run in the singularity, so in the containers. One example here, as we use the external distributed storage, is the NAKE 20 petabytes Tier 1 distributed storage, which is based on Dcache software, which is co-developed by NAKE, by DESI, Hamburg, and Fermilab. And so this is a store which is single point of entries, and where the storage pools are distributed among the 5 countries. So in this picture, you can see a traffic in and out of the storage. So to Vega, we could achieve almost 15 gigabytes per second of incoming traffic from the one. If you look at the nodes usage, so these are real applications. So the traffic from the Ceph storage was roughly 200 gigabits per second, but it was much higher from the Lustre, so it was close to 600 gigabits per second for this type of workflows. And here, just to show you an example how we use these resources in opportunistic, let's say, low priority mode. So this, the majority are the Atlas production jobs, while here the local higher priority jobs jumped into, and basically they got the resources, almost full resources, within half an hour. So this was a single user machine learning, let's say, job. So it's actually several jobs. So our goal is to go through modern HPC. So many users, especially the ones that are quite experienced with HPC, are asking for more flexible infrastructure. So for ease of access, remote connectivity, especially for data, for transparent data processing and data management as well. And they want to exploit the user community-driven orchestration. So they're not quite happy with the tools that are provided by the batch system out of the box. So for majority of users that are quite okay, but if they have a very complicated workflows. So let's say when you have a full chain of jobs that depend each on the other, organizing the execution node is not quite trivial. So many large communities have developed their own workflow engines, and they want to exploit this as well with the HPCs. By extending the classic HPC, so the classic in this sense means what was used in the last 10 years on most of the sites, there are many goals. So for example, we are providing a containerized job execution, mostly through Singularity at this point. And also the people that are used to bring their software, even optimized software through the containers. And typically we deliver software, as I told you before already, through with the CFS distributed file system. And they want to use also the cloud infrastructure. So we provide this for the moment with the Proxmox services with custom virtual machines that can be used to control the execution of the jobs on the HPC. And we plan to extend this to OpenStack in the near future. So also Kubernetes here is a quite high goal in a sense that Kubernetes is quite widely used by several users, communities, and even industry to organize their workflows, especially for the ones that they develop the workflows for the large public clouds, let's say like Google or Amazon. And they expect that such approach should be relatively transparent to port to the HPC as well. That's why we are also trying to collaborate with Atos on these new technologies. So a few words just on the resource allocation. So it was already mentioned before, what is the allocation policy for the HPC sites. And at this point, everybody is actually welcome to apply for Vega through the link I provided here. I think that Carolina is in the production as well. At this point, let's say that most of the calls are not still able to use all the resources owned by EuroHPC. That's why it's quite good that these regular production calls are coming, regular access calls are coming quite soon. But we still invite everybody who wants to do development and benchmarking to use these resources. There is also a very strong industry interest at this point, and some of the quite large interests would like to, they don't absolutely know issues with the payment or by using the resources. We've been contacted already by, let's say, I think more than 5 companies, and some of them quite serious. And it's interesting to point here that some companies actually take this as an using EuroHPC as an advertisement for their activities. So it's very good for them if they can show that they can use such huge resources. So just to conclude, so the Vega design has proven extremely efficient for various needs of our communities, and it's quite extensible with the modern technologies. A lot of them are, of course, still in development, but some are provided already. So the expertise with the distributed computing can be also extended for supercomputers. That's what I wanted to show a few minutes ago. And the modernizing of the HPC infrastructure is very high on our priority list, especially it's asked for the industry access. And I've seen from the previous presentation that it's quite huge overlapping goals where other EuroHPC sits, right? So I think that more coordinated activity on this would be quite welcome. I just provided you a few links for the documentations for the site itself, for the HPC itself, and for our National Competence Center. Thank you.
Thank you very much, Andrei. And from our side, I must say that both Northvolt, the large Swedish company, Kungliga biblioteket, and SMOE, they all have access through development to Vega, and extremely happy with the support we're receiving from you and your team.
Thank you very much.
Thank you. And with that, I would like to invite the next speaker, and that's Valentin Plugaro, the CTO of Lux Provide from Luxembourg. And Valentin will present us Meluxina. So welcome.
Thank you very much, Lilith. Thank you very much all for attending this presentation. So I hope you can see my screen now.
Yes, it is fine. Thanks.
Thank you very much. So I'm Valentin Plugaru. I'm from Lux Provide. I'm the CTO of Lux Provide. I'm delighted to present you what we are doing and the Meluxina supercomputer in particular. You have likely seen some of these slides if you have been part of other discussions that happened around the EuroHPC systems, but I will provide a review of it nevertheless. So Lux Provide was created as a new HPC center in Europe. It's the first one at the national scale for Luxembourg. Our core missions are to provide both infrastructure and the competencies to take advantage of that infrastructure. It's a supercomputing infrastructure, but also data. And the idea is to be able to provide services also to industry as well as to public research, academia. And not only on HPC topics, but of course to the spectrum of data, HPC and AI. We are of course hosting entity for the EuroHPC JU. We are also a member of the Competence Centers Initiative, the EuroCC project. We are located a bit north of Luxembourg City. Actually, it's in the center of Luxembourg country. And what you see in the picture on the bottom of the slide to the right is the data center hosting Meluxina. And our offices are quite close by to it. Meluxina is, of course, part of the European Digital Decade. As you all know, the idea is that Europe is boosting its capabilities, and this is reinforced now with the new JU regulations that provide even more funding and support for initiatives that are tied to supercomputing. The idea is that supercomputers are underpinning the digital strategy, and this is transversal for many fields. The EuroCC project, so it's of course not only about infrastructure but competencies, and we are proud to be a part of the Luxembourg EuroCC National Competence Center. In particular, what we are doing there is we are leading work packages for technology transfer, business development, and collaboration with industry, and we are interacting very deeply with the industry actors with different kinds of maturity to see what they need, how they could use HPC, and what are the needs where it's not necessarily HPC the one and only thing that they're doing, but it's part of a pipeline. And then HPC can be in the loop of things to accelerate where it's useful. And again, it's not just HPC, it's data analytics with the help of HPC or AI. We are joined in Luxembourg. We're a consortium of 3 partners from Lux Innovation, the National Innovation Agency, University of Luxembourg, and Lux Provide. And of course, we're also taking part into the Castiel project, so I'm looking how what other competence centers are doing across Europe and interacting with them. The main topic of today is to talk about Meluxina, so you will excuse me if I spend a bit of time on that. Meluxina, similar to most other HPC centers, HPC systems in the EuroHPC network, has been designed with some goals, with some key elements in mind, but is able to provide computing infrastructure, supercomputing and data infrastructure for a wide variety of workloads. And again, they can be computational, pure HPC, traditional HPC modeling and simulation, or more data-driven workloads. And the idea is also that you're coupling all of these things and you're able to do predictive analytics that are driving the computation that is done before. And all of these kind of things have to be embedded into the underlying architecture, of course, then have to be implemented into the actual supercomputer that you have. And overall, Meluxina, like the other EuroHPC systems, is targeting a high SLA and is built from ground up as a highly efficient and redundant system. In Luxembourg, there are some key sectors from mobility, financial services, health, space, logistics, and industry. And what we see Meluxina helping for all of those things. So the kind of use cases that we are seeing that Meluxina can help with are, for example, if you talk about space, you have this nice space weather forecasting. You're doing this by tracking objects on the orbit. You're looking at from imagery, you're detecting what happens, and then you're able to plan a launch that is taking into account all the elements that are in orbit. Or you can design better satellites. You can design better materials with applicability in space. You can collect data from satellites, not only with those that are pointing down, but also those that are looking on the orbit. If we talk about fintech, you can do things that were not possible before, such as a whole economy simulation, or doing things that are a bit traditional for finance, like portfolio simulation and management. But you're bringing it to the next level. You're able to do it much faster, or to consider more elements than you were able to do before. Engineering and materials, this really needs no introduction, but I think at the European level, there's a lot of push for digital twins, from virtual testing of prototypes to seeing how things will behave, simulation of factories, digital pilots, all of these things that are coming up as key elements for the next decade. And then there's all the other things like climate and weather, which is again very typical for supercomputing to do. We've seen this year with a lot of flooding and other kind of disasters that maybe on which we hope to be able to improve on. So from simulation of new things happening to being able to do earlier prediction and to in the end to save human lives and to save infrastructure that can be affected if you don't do something in time. Smart cities, so well, everything is smart cars, smart cities. The idea is to be able to improve design for new construction, new simulation, to do better planning, all of the things that are really going to push us forward. And for personalized medicine and healthcare, really, I don't have to talk too much about this. Supercomputers have been used now for COVID-19 since the beginning of the crisis. And we have seen the capabilities that supercomputers can bring into this field. Now, Melusina, again, was designed from ground up to respond to these kind of needs, and also things that are likely to come. Melusina has a modular approach. There's different modules with different kind of capabilities behind. There's the main computational parts are in two main modules, cluster and accelerator. Cluster module, it's composed of CPU-only compute nodes, while the accelerator module has GPU AI accelerators inside, but also a tinier partition with Fpga nodes for specialized workloads. There's also in-memory computing capabilities on a large memory module. And all of these computational modules are tied into a common fabric with a tiered storage underlying everything, and then tied, of course, into the system module that's providing the logic of the system, the workload management scheduler. But there's also a cloud module which has some initial building blocks. It's an OpenStack cloud in the end, where we are able to provision things that cannot be encapsulated in a traditional HPC batch job. Databases, APIs, web portals for new use cases, both to orchestrate the workloads or to do data, provide visualization or do analytics, things that are again piloting or providing extra to what the main computing can do. Melusina, the Melusina architecture is implemented with an Atos machine, with the Bull-Sequana system, and we are also supported by the Parastation modular software stack from Partech. The building blocks are AMD EPIC CPUs inside the system, NVIDIA A100 Ampere GPUs. There's roughly half a petabyte of RAM inside the system, 20 petabytes of tiered storage. There's an InfiniBand HDR 200 gigabit full HDR fabric in the Dragonfly topology, and the software stack on top, on which I will spend a bit more time in a later slide, is done with EasyBuild, but we're keeping an eye on the EC project as well. In terms of core capabilities of the system, so if we are looking at the peak aggregated performance of the system, we're arriving to somewhat above 18 petaflops. But the accelerator and accelerator module is, of course, providing the main performance, the main capabilities of the system. So there, it's above 10.52 petaflop mark reached in HPL, although the system for AI workloads, so in lower precision, is reaching 500 petaflops of AI performance. The cluster module, of course, has more compute nodes, but is more modest in sustained HPL arriving above 2.25 petaflops. But again, it's all-purpose, where all the applications that users could want to run are able to run, not only specialized accelerated workloads. There's a nice FPGA partition as part of the accelerator module, which contains FPGAs, and this is we're looking forward to what users are going to be able to do with that. It will be mostly for specialized workloads. It could be streaming analytics. It could be real-time decision making. We're really looking forward to see this being used. And again, the third computational part is the main computational part is the large memory module, where each compute node has 4 TB of RAM per node. So that's quite a lot more than a regular cluster node. On the storage side, we have raster file systems right now in different tiers. So there's 3 mainline tiers, and then there's a tape archive in the back. So we have roughly half a petabyte of all flash as an acceleration tier, which provides above 400 GB per second in throughput, read and write. And this is meant for very intensive I/O, either doing analytics over data sets where you need to train some neural networks a lot, but it can also be used for application checkpointing, long-term, where you're able to split a long-term workload into several jobs and then restart from the latest iteration. The main storage tier is the tier 1, or the project tier, like we call it inside. It's above 12 petabyte of storage. That is, it's capacity tier, but also performance. So it's around 190 GB per second. It's all purpose, and compared to the number of nodes, we have a very, very good throughput for the number of regarding the ratio between compute nodes to storage performance. There's two tiers dedicated more towards backup and archival processes. The tier 2 backup tier of something like 7 petabytes can provide some redundancy for projects that may require it. And then there's a long-term archive that is the initial building block is 5 petabyte that can be extended to 100 petabyte to sustain a long-term archival for reproducibility or legal aspects. In terms of interconnect, I already said we have this InfiniBand HDR200 in Dragonfly Plus, but there's also a very high-speed links with the JAMP network through the Restena and REN of Luxembourg. Actually, there we have 2 100 gigabit per second links, so we are able to have a very good throughput and exchange data very well to the other EuroHPC sites. We also have redundant ISPs with high bandwidth, and we're also deeply connected to the Luxembourg Internet commercial exchange backbone with high bandwidth redundant links. Okay. Meluxina was happy. We were happy to rank Meluxina in the top 500 and other 500 other rankings this June. We came out with a very good spot for Green 500 in terms of efficiency of the accelerator module, number 4th worldwide, first in the EU. In top 500, where we were at the time 10th in the EU, 36th in the world, but also because we were using a very deep analysis through our acceptance processes. We had other numbers to show in terms of graph analytics, where we're coming up 10th worldwide, 21st in IO 500, and 28th on the HPCG benchmark. A few more details, but although I'll not spend too much time on this, on the actual components on the compute side. So we are AMD EPYC CPUs, and again on GPUs there's NVIDIA Ampere. One thing that we wanted from the beginning was to have a high memory to core ratio, not only for current workloads that are maybe a bit less intensive, but also for future workloads. And you can really, each compute node is really packing a punch. So for many things, you don't even need to spread out and do ultra large scale simulations, because you have enough capabilities per node to do that. The CPU nodes are single rail HDR200, while the GPU nodes are dual rail HDR200. And then there's 4 NVIDIA A100 GPUs with 40 GB of memory, of high bandwidth memory on them, with this 3rd generation tensor cores providing mixed precision support. We have different CPUs on the GPU and the Fpga nodes versus what's on the CPU and large memory. That's because on the accelerated nodes, either with GPUs or with FPGAs, we're counting on the accelerator part to be the main deliverable of the compute node. Like I already said, the large memory nodes have a similar to the CPU nodes, just a lot more memory, so 4 TB of RAM each. And there's some local storage on the accelerated on the GPU nodes, large memory in the FPGA, which can provide some extra help if some data needs to be staged to the nodes to provide some local storage. The FPGA nodes have inter-Stratix FPGAs. There's actually 2 of them per node. There are Stratix 10 MX cards with the 16 GB of high bandwidth memory on them. So again, we're looking to see what people will be able to achieve with them. The cloud nodes, so it's an OpenStack cloud. They're very similar to our compute nodes. They're even linked into the high bandwidth fabric, but for now we're just using the Ethernet network, and they're separated. They're not accessing the fabric directly. But future use cases may be able to use the InfiniBand fabric as well. We are seeing to deploy some at the center level some tools for visualization and some portals. But end users may be able to use individual VMs that are in where they are controlling the software stack that they install. And about the software stack, the Melusina user software environment, or the MUSE, we're doing this with EasyBuild. The goals were, of course, from the beginning to be able to provide tools to take advantage of the infrastructure, keeping them closely recent to what's the state of the art, but also maintaining them such that across 1 year or 2 years, you can consider software stack a big production. And then the challenge is, of course, that we have Zen 2 CPUs, Ampere generation GPUs, and Stratix FPGAs. So the idea is to be able to deploy this software stack and upgrade it as a whole. This we're doing with EasyBuild. We're still keeping a close eye on SPAC and EC projects. We will use we are using LMOD modules and the reframe for functionality test. And for the software stack, it's quite rich in the sense that it provides all the necessary building blocks to either bring your own code and compile it, test it, debug it, and run it, or to find already some tool that you may already need to use from molecular dynamics, GROMACS, Quantum Espresso, or CFD, OpenFOAM Extend, and others. There is a lot of compilers that support the latest standards. So the AMD optimized one, the pure GCC, the NVIDIA Hpc SDK, which contains the PGI one, and also support for different programming languages from Python to Julia, Go, R. Different MPI suites, math libraries, data libraries, and frameworks, traditional frameworks for AI such as PyTorch, TensorFlow, but also big data such as Apache Spark. We will have performance and debugging tools from Intel, NVIDIA, and the ARM with the ARM Forge toolkit, DDT, and MAP. And for visualization of results, there's several toolkits, ParaView and VMD are already there, and I think we will provide a visit as well. Containerized workloads, like it has been said before, Singularity containers are now very standard. We will have them as well. We're still testing NVIDIA nRoot and PyXis tools as an alternative, and to see which ones users are taking advantage of. Melusina is hosted in the LuxConnect data center. Melusina is linked to the different, is coupled to different power supplies and so on. The data center is a tier 4 certified data center and ISO 27001 certified as well. And we are also aiming to be ISO 27001 certified, which is a process we are already going through. Some pictures from earlier this year, with the arrival of the main hardware components. On the bottom, actually in the center, you can see a GPU node with the 4 Ampere GPUs and the 2 CPUs to the left, plus the fabric in the back. If you would visit Melusina today, this is what you would see. So this is the face of the system, and of course, behind the Melusina Mermaid, you have the actual liquid-cooled compute modules. while those are, of course, the accelerator and cluster module, while the rest, including the system logic, cloud module, and storage, are on an air-cooled or air-cooled technologies. What's next for us? So we hope to see amazing science and innovation being done. We look forward to providing the access for our early access users and the first benchmark and development calls from the JU. So that's it from me for now. I hope it was interesting for you. I look forward to the questions that you may have, and I'm handing over back to our organizers. Thank you very much.
Thank you very much, Valentin, for an interesting presentation. Obviously, your system is very attractive for AI, ML applications especially. So we're looking forward. And the next speaker is Branislav Jancic from IT for Innovations, the Supercomputing Services Director. So Branislav, the floor is yours, and you will introduce Carolina.
Okay, thank you very much. So thank you very much for the introduction, and thank you very much for the opportunity to speak here. I will introduce the Carolina Supercomputer in the context that is being hosted at IT for Innovations National Supercomputing Center. First of all, let me introduce a little bit of context of the IT for Innovations National Supercomputing Center. Basically, the IT for Innovations has been established in 2011 in Ostrava in Czech Republic. That is, when you look at the map, it's up here on the northeast part of the Czech Republic. The IT for Innovation is a unit of the VSB, Technical University of Ostrava. It's basically a research institute at the VSB. Within the Czech Republic context, the IT for Innovation is a member of ENCCS, a strategic research infrastructure that is operating e-services across the Czech Republic. We are operating 4 supercomputers at the moment: Salomon, Barbara, NVIDIA DGX2, and Carolina Supercomputer, of course. And we provide our services to Czech Republic, but also to the European Union, basically via PRAISE and via EuroHPC. We are not only operating the supercomputers, but we are basically a research institute. So we host 5 research laboratories, all of them very closely with hosting a research very closely related to high performance computing. So in total, we have over 130 FTEs, and also due to the laboratories present, we have a large amount of expertise accumulated, large amount of HPC expertise accumulated basically within the building. So this is a picture of our building in Ostrava that is hosting the supercomputer and the research laboratories. Basically, this green part out here, that is where the computer room is located. We participate in a large number of European initiatives, including of course, the EuroHPC, the EU.ETP for HPC, BDVA, and so on. We have a very strong international collaboration. We are currently involved in 14 Horizon 2020 projects, and we have a strong collaboration with industry. We also always maintain a strong curriculum of training and educational activities, averaging about 10 to 12 training events a year. Okay, let me look at the infrastructure. Basically, the infrastructure at IT for Innovation is organized like this. On the top, we have the connectivity. We have the WAN infrastructure. It's all based on 100 gigabit technology, and we have multiple 100 gigabit links that are connected to the backbone network of the NRAN network in the Czech Republic, with a very strong connections to JAM and to all the other academic networks and also commercial networks that are surrounding the Czech Republic. So the connectivity is very, very strong. And to this central point, we connect our supercomputers, and we also to this point also connect the centralized storage that we call a project storage that serves our supercomputers to keep the project data. And then we have our supercomputers, the Carolina supercomputer, the Salomon supercomputer, the Barbara supercomputer, and the loosely integrated into the Barbara, the DGX2 computer. And they are all served by this centralized infrastructure, the network and the centralized storage. let me have a look. Let me focus now on the Carolina supercomputer. So, but before I do that, I will say a few words about the project storage, because that is basically serving services to the Carolina, and the Carolina users see the project storage. So the project storage basically is a very nice independent piece of hardware that was constructed in such a way that it's extendable, it's scalable in size, and it's highly redundant. We are basically, via this project storage, offering 3 times 5 petabytes of storage capacity with aggregated almost 40 gigabytes per second, and this storage capacity is via the NFS protocol to the other supercomputers. And now, finally, let me look at the Carolina supercomputer that we operate. So these are some pictures from the computer room of the Carolina supercomputer. The Carolina is now in place and operational, and is hosting the first users. Well, basically, if I look at the timeline, we have started with installation of the Carolina supercomputer in December 2020, where we opened the computer room and started the first works. In January, the computer was really brought in place and connected to the water, to the electricity, and so on. And some finishing works were done since then. The partitions were brought in, including the accelerated partition. In April 2021, we had a partial acceptance, and we fully accepted in June 2021. Now the computer in the computer room and operational. Let's have a look at the architecture, what Carolina actually contains. This is a very simplified picture, simplified view of the Carolina supercomputer, and basically the dominant part are the 4 partitions that we have here. First of all, we have a universal partition that contains 700 CPU nodes and over 92,000 cores. What these are, I will talk about it later. Then we have an accelerated partition that contains not 70, but now 72 accelerated nodes. And all of these nodes are accelerated with 8 A100 GPU accelerator cards. Then we have a data analytics partition. It's basically a single node with very large memory. It contains 24 terabytes of memory basically in the single SMP Luma computer. And then we also have a cloud partition, which is providing over 4,600 cores and 9 terabytes of RAM. The configuration of this hardware is very similar to this universal partition, where we plan to host the cloud services. All of these partitions and the storages that we have, where the important storage here that is tightly connected to the computer is the scratch storage, which is special with the performance of over 1 terabyte per second. I will talk about it later. All of these partitions and the storages, including the home infrastructure and backup storage, are connected to each other via the LAN network, which basically serves for administration purposes, but also, most importantly, via the InfiniBand HDR network in a full FAT3 topology. And then the Carolina supercomputer via dedicated gateways is connected to this 15 petabyte of the project storage. This project storage then via this gateway and via the compute network is accessible down to the individual compute nodes at the Carolina supercomputer. So this is the overall architecture. Let's have a look at the individual partitions. If I look at the individual partitions, the universal partition, 720 servers, it's HP ProLiant servers. They are equipped with AMD EPYC processors and 256 gigabytes of memory, and they are connected to network with HDR 100 connection, that is 100 gigabit connection. We operate there a CentOS operating system. This partition has over 3.8 petaflops in peak performance. However, if I look at the individual compute nodes, the individual compute node that you find here, the performance of the individual compute node is also quite impressive. The two AMD EPYC processors, 7H12, I think that most parties at the EuroHPC have very similar processors. These can actually serve over 5 teraflops in double precision performance, provided that you of course use FMA fused multiply add instructions. This performance is not only theoretical; it can be really achieved in flash, so to say, in practice. Of course, the impact performance will be little bit lower than this performance that we have obtained via basically a special dedicated micro benchmark. It's of course not only about performance. What is very important for us is the memory performance, because many of the applications will depend more on the memory performance than on the actually the processor performance. Due to the fact that we have AMD EPYC processor, these processors are basically split into number of NUMA domains. They are split into the chiplets, and these chiplets, they form a NUMA domains. Nevertheless, the performance is really impressive. We observe something like 25 gigabyte per second per NUMA domain in this processor. And overall, we basically in the stream benchmark, we could see the aggregated performance of over 200 gigabytes per second. The NUMA effects, they may be significant. That means that if you read the data from the NUMA domain, from some NUMA domain, and processing the data on the other NUMA domain, you can see the NUMA effects. You can see the sort of the NUMA distance. This is the NUMA distance matrix. It may look a little bit scary that basically if you go from one socket to another, the performance will be something like 3 times lower. The reality is actually not that bad. We could see that if we measure it, that the NUMA domains are the NUMA effects on this processor on these nodes are almost negligible. Good. However, the main portion of the performance comes from the accelerated nodes. We of course have also to complement the universal partition and the universal nodes. We have the Cloud Partition. The Cloud Partition contains basically 36 nodes. They are of the more or less the same configuration as we have the universal partition. The main difference is that they are also equipped with NVMe storages, and they have 10 giga. They have, in addition to the HDR interconnection, InfiniBand HDR interconnection, they have also Ethernet interconnection that allows us to build custom networks within this virtualization infrastructure. The main portion of the performance, however, comes from the accelerated nodes, and we are a little special compared to what is typically observed. We have the accelerated nodes that have 8 GPU accelerators on the node. So we have 72 of these nodes. They have the EPYC processors, and however, we have 8 times NVIDIA accelerators and 1 terabyte of RAM memory. In addition, these nodes are very strongly interconnected with 4 times 200 gigabit per second interconnection to the InfiniBand network. The whole partition has a peak performance over 11 petaflop. Where the performance really comes from are the accelerator cards, and here we are again a little bit standing out. The accelerator cards are connected together via NVLink. However, this is a switched network. We have an NV switch that is switching the connections between these cards. The effect of that is that we can use the unified memory the unified memory approach, the NVIDIA unified memory, and the accelerator cards can see via this network into the memory of the other cards without interfering with the concurrent accesses from the other cards. That's the property of this NV switch, and we could see that this effect can be actually very, very strong. So this unified memory makes this very, very, very powerful, because suddenly we don't have only the individual 40 gigabytes per card, but we can see the aggregated memory across this cluster, and moreover the efficiency of the connection and the efficiency of the memory access from one card to another can be very high. These cards are also extremely powerful. These are some numbers from basically from the specs. However, we have seen exactly these numbers in flash. We have obtained these numbers in dedicated micro benchmarks. We could see that the double precision performance of these cards can go up to 9.7 teraflops. And when doing the tensor operations, we can obtain up to 19.5 teraflops per card. Well, of course, these performances depend on what precision you are using, whether you use the 64-bit precision or whether you use some lower precision, and what format, what is the particular format. There is a strong dependence on that, of course. However, we can confirm that these performances are there and are actually sustainable in reality. When we look at this from practical point of view, the 8 NVIDIA cards that we have, we can basically obtain, and we have seen this in real computation, when, of course, using FMA, fuse multiply add instructions, we can see up to 77 teraflop in performance for double precision. When you go to tensor operations, when you employ the tensor cores, and these basically do matrix multiplication. So whenever you have applications that depend dominantly on matrix multiplication kernels, then this regime can be used. Then these 8 cards can spit out basically up to 150 or over 150 teraflops in performance. Of course, if we go to reduced precision, to the half precision, and use the tensor cores, we can go over 2.4 petaflop in performance, basically in a single node. The HBM memory is also extremely performant. In the stream benchmark, we can see that in a single card, we can go over 1,300 gigabytes per second and over 10,000 gigabytes per second in aggregated throughput. The NUMA effects when going from one card to another card is approximately the NUMA metrics can be written like this. So compare when you go from one card to another, with the memory throughput is approximately 4 times lower. However, it's still very high number compare if we start from 1,300, so it's about 4 times less. However, it's still basically more than you would see on a regular processor. The data analytics partition is also very interesting because it's a big shared memory system. It's a HP SuperDOM Flex. It basically consists of 32 Intel Xeon processors that are interconnected in all-to-all topology by a NUMA network. In total, we have over 24 terabytes of memory on this node, and this node also has high connectivity to the network and high connectivity to the scratch storage, 2 times 200 gigabit per second HDR InfiniBand. The peak performance of this machine is almost 70 teraflop, and of course, in reality, in impact, it's of course less. However, we could see that almost 62 teraflop has been obtained in the micro benchmark. And when we look at the memory performance, is also very impressive. Basically, in one NUMA node, in one single NUMA node that we have here, we have the performance approximately 80 gigabytes per second, and then this can be multiplied basically by 32 for the total performance for the memory bound codes. The NUMA matrix is, of course, the NUMA effect is relatively strong. The neighboring compute node, the neighboring nodes can have basically 1.6, and going to the far node of the NUMA domain, the memory throughput can go down by factor 4 approximately. The InfiniBand network is also very powerful. We have a basically non-blocking FAT3 interconnection that is based on the HDR200 technology. We are using splitter cables for the HDR100 interconnections to the compute nodes, but otherwise it's fully HDR200. The latency is less than 3 microseconds. And well, the throughput that we really see and that we really observe in MPI applications is approximately 11,500 megabytes per second. That really corresponds to this 100 gigabit per second link speed. What is also very important for the memory bound applications and for the data bound applications, it's important that we have very good access to storage and that we have a high performance storage. So we have a basically cluster store E1000 all flash storage. Our vendor actually commented that this is not a scratch storage. This is just a big burst buffer. Yes, it's a big burst buffer. It has a size of 1.3 petabyte, and we achieve the throughput to this burst buffer over 1,200 gigabytes per second. This is basically on the Lustre file system. And this picture here shows how the building block of this storage looks like. Basically, the storage units are these SSUF units, and these are practically a compute nodes or nodes with the 2 processors and then equipped with a large amount of flash memories to store the data.
Branislav, I'm sorry, we have
Yes,
3 minutes left.
And I am right at the end. I'll just like to summarize that the Carolina supercomputer is highly powerful. We rank number 69 worldwide and 19 in Europe. But of course, keep in mind that this is only the accelerated partition ranking. If the ranking would be, if it's possible to rank the aggregated performance, we would rank somewhere at number 40. We rank number 15 on the Green 500. Basically, I would just like to mention that the Carolina EuroHPC, that the Carolina is accessible via the EuroHPC benchmark and development calls. And basically, we are the resources that are written out here. These can be allocated per project. We expect to support 20 plus 20 projects in each call. And last thing to mention, all the details how to use the Carolina, all the rich environment over the 1,000 modules, the 1,000 software modules, the compilers and the tools and the tool tips and tricks and how to use the Carolina supercomputer is documented in detail in our documentation. So please go and visit the documentation. You will get the practical knowledge to use the Carolina in operation. Good, and that is just the last slide. Thank you for your attention. The Carolina supercomputer is now reaching over 9.1 petaflops in impact accelerated. It's massively accelerated computer with 8 NVIDIA Ampere cards per node, and it's already fully accepted and in operation. Thank you very much for your attention.
Thank you very much, Branislav. And so I would like to invite our next speaker, Professor Ivan Dimov from Academy of Science in Bulgaria, who is the head of the Department of Parallel Algorithms, and he will talk about the Discoverer, the supercomputer in Bulgaria.
Okay, so I will try to briefly present the Discoverer petascale supercomputer. It has 4.5 petaflops, which is based, as you know, on LINPACK benchmark. You know that some people are considering also some other measures, but you may know that even today is about 91% of usage of supercomputers in the world are connected to solving linear algebra problems. So from my point of view, it's quite good measure for the performance. Very briefly, Discoverer is ranked at 91st place among the world 500 supercomputers. and similar to other petascale EuroHPC supercomputers, it is funded by 35% by EuroHPC joint undertaking and by petascale super consortium Bulgarian, and also by the Bulgarian government. Very briefly, I will tell you that Petascale Bulgaria is a legal consortium combining knowledge and 15-year expertise and National Center for Supercomputing Applications, the Strategic Center for Artificial Intelligence, Institute of Information and Communication Technologies at the Bulgarian Academy of Sciences, which is hosting another supercomputer in Bulgaria called Avitohol, and also Sofia Tech Park, where the Discoverer is hosted. So Discoverer objectives are to foster better science within the society, to facilitate cross-border collaboration between academic institution and industry and business, and to help training the next generation of Bulgarian and European IT talents. Something about system architecture. It contains 12 direct liquid cooling racks. In each rack, it's possible to have 32 blades per rack. So Discoverer has 376 blades. Each blade has 3 nodes, which means there are 1128 computing nodes. Each computing node contains 2 AMD EPIC processor. And what is also important that it means that there are 2256 CPUs, and each of them contains 64 cores. So roughly speaking, the number of cores are 100, a bit more than 144,000. Total size of the RAM reaches over 300 terabytes. What is also important to say that fast disk storage is more than 20 gigabytes per second, and internet connection is done with InfiniBand 200 gigabits per second. It's also maybe important to say that the whole system weight is over 30 tons, and total power consumption is 1.3 megawatts, including infrastructure. Some information about software and target application areas. The software is oriented to users, mainly from the Bulgarian academic society and industrial society, which is using supercomputers. So it's focused on software based on bioinformatics and genomics, computational and quantum chemistry, molecular dynamics, mesoscale modeling and Monte Carlo methods, computational fluid dynamics, and AI, big data analysis, and so on. Talking about application areas, the computational society in Bulgaria is mainly focused on in silico drug design discovery, structure property preparation, molecular discovery, digital product formulation and optimization, climate and weather forecast and environmental modeling. There are groups putting a lot of energy and big number of projects in this area. Simulated environment and also financial studies and market studies. So something about discoverer access policy. It's absolutely synchronized with the access policy of EuroHPC. The main resource, about 80 to 90%, will be allocated for regular HPC projects, and another 10% will be allocated for fast-track applications, which is an important part for us. Only few percent will be allocated for HPC project benchmarking and for software development. The calls, EuroHPC calls, will be organized via praise and are targeted pan-European HPC project, including accessing to applications, and the applications are split with this ratio 80/20. As it is considered as a policy of EuroHPC. Petascale resource share is 65%, and it will be allocated using similar, as I already said, similar to EuroHPC access policy. We have already established a scientific and applied board, which will be regulating and organizing this access policy. For both EuroHPC, which is 35%, and Petascale consortium will have 65 share. In addition, maximum 80 to 20 split between scientific profit and non-profit and profit organization. So here, since I don't have much time, I will show briefly some important projects and applications just by sharing some pictures. The applications now are running on Avituhol supercomputer, but there is agreement between Discoverer and Avituhol to move the applications I'm showing to Discoverer supercomputer. There are applications. First three applications are connected to studying of problems of transport problems via porous media. The problems are very important because you need to deal with fractional derivative formulations of partial differential equations. Then you have applications connected to local weather forecast and climate modeling. Then you have applications connected to computational quantum physics. Another class of applications are connected to nonlinear vibrations used in application to using drones and other things like that. And last applications are connected to biology and medicine, studying RNA things and things like that. Another kind of application is quantum computing. So here we have a very strong collaboration with the University of Montreal, Quebec, and we work together. Applications like that will be also run on Discoverer supercomputer. There are some other quantum computing applications. They are based on so-called sign particle formalism for quantum computing. And this is almost all I wanted to say. And before to conclude, I would like to say that our main goal is to try to find synergy and merge together practice with theory and industry with academic science. So before I finish, I would like to show you two interesting statements of two important people. The first one is there is nothing more useful for the practice than the good theory. And the second one is, in theory, the theory and the practice are one and the same. However, in practice, they are not. So thank you very much for your attention.
Thank you very much for your presentation, Ivan. And I guess that brings us to the last speaker. And I would like to present João Barbosa from Portugal. He's the research engineer at Minho Advanced Computer Center, Portugal. So João, the floor is yours.
Thank you so much. First of all, let me thank the organizing committee for this wonderful workshop. It's been enlightening. I'll be the last speaker. Most of the things that I'm going to talk about, some of the other speakers have already talked about, but that's the consequence of being the last, I think. My idea is to give you a little bit of a brief history of what MAC has been, what it's been doing, and what our goals for coming along. So MAC started as National Supercomputing Center about 3 years ago. The main idea was to provide to Portugal specific advanced computing capabilities that were not available in place. So that was our goal, especially to support both the academic institutions as well as industry and industry partners, as well as the public service entities in Portugal. So the goal was to start creating that capability that was not available, or if it was available, was distributed across the country. So it was created basically 3 years ago, and we're on the north of Portugal in the region of Minho at this moment. We are providing already a couple of capabilities, both HPC and cloud computing, delivering to the users all the services that they need. Our capabilities have been growing in the past year, will grow faster with Ducalion, that I'm going to talk a bit more later. Our idea was to provide support for several key research areas within the country, both through digital simulation and the creation of digital surrogates, as well as creating capabilities for data science that was not available at the time. Basically, we have 5 pillars that we much impose into the organization and the organization culture. We are foremost an HPC provider to Portugal and now to Europe through the EuroHPC initiative. We are also a research advanced computing center, meaning we also do research into advanced computing, especially targeting exa-scale capabilities and developing exa-scale software stacks for several fields of science. We are also keen on doing human resources training, especially in HPC. One of the problems that existed in Portugal was the lack of HPC knowledge. So that has been one of our focuses. We've been promoting heavily HPC across the country. We've been doing training sessions from HPC to AI, machine learning, all sorts of fields connected to HPC, as well as doing specific workshops to promote user interaction in our systems. It's not only us telling what is the most efficient way of using the system, but it's also having the users come back and tell us what the problems were, telling other users how to overcome them, and so forth. And then support our public institutions and companies in several ways, and helping them to come into the HPC generation, as well as promoting internationalization of our resources. We did this by bootstrapping Mac with a system that was called Bob. Bob was a gentle donation to us from a US system. It had roughly 10,000 cores that we're still operating and that we're still delivering into our community. And as I said, we are in the north of the country, so our data center is localized there. And then again, our fields of application go through basically all fields of science, from bioinformatics, fluid dynamics, materials, molecular dynamics, physics, chemistry, medicine, health. I'm not going to bore you with more details since other speakers already talked about it. And we focused on delivering key services like storage, databases, distributed computing, special software stacks for message queuing, data warehousing, modulation, visualization, queues, and so forth. So the system has been operating since the end of 2018, more or less, and we've been constantly growing and delivering more core hours as more users come into the system. Right now, we are operating roughly at 60% capacity. We have been increasing ever since the center was created. More and more users are attacking the system. We are now roughly within the thousands of users using the system within Portugal. And again, our main goal is to efficiently deliver software. So these are some of the examples of the projects that we've been working on and that we worked on with some of our researchers. They go from particle physics to climate change, industrial applications, especially in plastic molding, fluid dynamics for healthcare, and so forth. Not only that, but one of the goals of the center is always to allow users to come into the system, especially having focus on what the trend is, and we are going to exa-scale. There's no doubt that in the future we'll have these massive computers coming in, so we need new ways of tackling the application at that level. So one of our key researches is helping users modernize their code, having exa-scale in mind, and one other feature is bringing in visualization capabilities into the software stack while using the simulation, so that we can do both things. One, minimize energy costs of doing post-hoc visualization and analysis. The other one, to allow for computational steering. Exa-scale poses a huge challenge to researchers. They will be massive simulations using huge amounts of CPU core hours during long runs. And they need a way to have analysis embedded into their simulation so that they can either tweak the simulation as it runs along or to kill it just because it will explode on itself. So one of our key challenges is to actually target this type of application and develop new techniques with our partners, both in academia and industry, to tackle exa-scale in a consistent and fair way. Having said that, we're growing. We are going to launch Deucalion. It's going to be a roughly 10 petaflop supercomputing. It will have next generation x86 partition based on AMD EPYC processors, doing all the computation that we're doing. So we're basically taking our existing software stack and just porting into this particular partition and letting the users run it. But we also want to, since one of our goals is to enable exa-scale, that's one of our core principles. We want to reach there. So we are actually going to go with a state-of-the-art ARM processor from Fujitsu, the AFX64. It will be a part of the system, so they will be more or less 50-50% of the CPU cores available on it. Because we cannot forget accelerators, and we want to deliver to our community of users the capability of using GPUs not only for machine learning but also for HPC and large-scale simulations. We are heading roughly 10% to 10% of the nodes, the x86 nodes, will be adding GPUs, namely the AMD VOLPA Ampere, the latest generation available. It will be deployed with the x86 platform. We are also looking into some more exotic architectures to place into the system so that we can do some experiments. So we are going to dedicate a little bit of our rack space into those architectures, enabling the system to the users to experiment with other architecture that are not our typical x86 or ARM architectures, or the GPU architecture for that matter. So we'll be playing a little bit with it without that. Of course, data system cannot operate without storage, so we're deploying dependable and highly efficient storage system, basically with 10 petabytes of capacity, net capacity in total. They will be divided between Scratch systems, highly efficient IO bandwidth system, and a more long-lasting storage for project storage and so forth. But since, again, one of our goals is to be a platform for enabling exa-scale, one of the things that we are very conscious about is power consumption. So we want to be extremely efficient and delivering not only the hardware, but also the software stack. And going beyond the data center itself and going to power generation. So we have a project attached to our data center that is going to produce energy for us based on renewables, recycling energy, reusing energy, and so forth. So we'll have a complete integrated monitoring energy system into the data center so that we can try to achieve an efficiency of 1.1. That's one of our main goals with the system. And for that, we have to deliver some kind of strategy. The x86 will be the de facto standard. So we are hoping that the users, when the system comes online, will use that partition as much as they can. All the software stack and all of our expertise will be there. And we are now developing expertise in collaboration with Fujitsu to port efficiently the software stacks that we already have, and some of our big users into the ARM system and helping them along with Fujitsu to build capacity to actually exploit efficiently the ARM system and leave behind some of the pitfalls that usually drive from migrating from an x86 platform to an ARM system. We are doing that consistently, either operating with Fujitsu, but also doing training. So one of our training events is called MUG, our Mac user group workshop. It is composed by two parts. One where we invite leading experts on certain technologies to give talks and to give training. Our last event, we had both Fujitsu, ARM, and NVIDIA coming into the workshop and providing not only training, but also expertise and answering questions and doing a little bit of a hackathon in the middle. But we also have users coming in and telling other users what their experience is, what their thoughts are, where they stumbled, how they were able to overcome those obstacles, and so forth. So it's always a double sword strategy. One, work to develop new techniques, to work to train our users to use them. So the Calendar was awarded in 2020. Unfortunately, due to some unforeseen problems that we had with the data center, the building is a little bit late. So we are hoping that the Calendar goes live in the first quarter of 2022. So that's our main goal right now, somewhere in that first quarter to launch Ducalion into the world. This is basically our team right now. We are growing and we're growing fast. There's a couple of people that are coming aboard. We are also hiring for anyone that wants it. And right now, we are doing our best to help our users. And that's basically what I have for today. Thank you so much for your attention.
Thank you for your presentation very much. And I guess that was the last presentation for today.